Right, good afternoon everyone. So today we're going to look at redox reactions. This is what you did in grade 11, and then we're going to go on to see how this applied to cells. So let's just talk about a redox reaction. Can anyone tell me what is a redox reaction? Yes? It is a? Yes, perfect answer. It is the transfer of electrons, right. If you look at redox, the word redox is actually showing to you. It's got both reduction and oxidation happening at the same time, right. Now, what is oxidation? Now, some of the guys use oil rig to remember that, hey? Most of you maybe. Right. Because oxidation is the loss of electrons. So if something gives off electrons, it is oxidizing. While reduction is the gain of electrons. So if it takes in electrons, it binds to the electrons, then it's reduction. So a redox reaction is a transfer of electrons. Now, if I look at an equation, I have to be able to see if that is a redox reaction. So just quickly turn back to where we did acid and base reactions. Just go and look at page, I think it was 21. Can you just quickly turn back to 21? Now there we had 4 reactions. Now this first reaction, it was the reaction of a metal with acid, a metal and an acid. A metal and an acid gave salt and hydrogen. Is that a redox reaction? Is that a redox reaction? The answer is actually yes. Why is it yes? Because there is transfer of electrons, right? How can I know there's transfer of electrons? Because on this side, the zinc over there has got no charge, right? And on the other side, it's part of salt. So it will be 2+ on the other side. And the only way that it can change that charge is by giving off electrons, right? So yes, this is a redox reaction because there is electron transfer. How about the second one? Is this a redox reaction? No, no. We call this an ion exchange. An ion exchange reaction. Because what happens is this positive ion is bonding to that negative, and this positive is bonding to that negative, but nothing is changing. No charge changes, right? So there's no transfer of electrons. The ions are just swapping positions. So this is an ion exchange. It's not a redox reaction. So you have to be able to look at it and see. How about the third one? What is this? Is it a redox or is it ion exchange? It's ion exchange. The zinc is already 2+ and it ends up 2+. It's not changing, right? It's just swapping places with the hydrogen. It's bonding to the chlorine. So if the charges doesn't change, it means no electrons were transferred. It means it's not a redox reaction. And then usually it's an ion exchange reaction. Right. Okay, so let's think about redox reactions. Think about, say for instance, you've got magnesium reacting with chlorine gas. What do you expect the product to be if you've got magnesium reacting with chlorine gas? Magnesium chloride, nice. Magnesium chloride. So this is what you expect to have as a product if magnesium and chlorine react. Now in this one, we start off with magnesium. Now if I only look at the magnesium start off with a 0 charge, and afterwards magnesium is part of that salt. What is the charge of magnesium over there? 2+, right? 2+. It's in a bond. Right. Now, how does the magnesium become a magnesium 2+? Did it release any electrons or did it gain electrons? It released electrons. Now, if you're not sure, remember we have conservation of charge. So the total charge on the left-hand side must be the same as the total charge on the right-hand side. On the left-hand side, the total charge is 0. So the electrons must be over there so that the total charge on the right-hand side is also 0. It's the only way to have conservation of charge. Now, if I do look at this, what do we call it in science if electrons are released? This is my oxidation, and now this is a half reaction. Why do we call it a half reaction? Sorry for the spelling. Okay, half reaction. Why do we call it a half reaction? Because that reaction on its own can never occur, right? You don't have extra electrons on your shelf that you can add, or you can't store extra electrons somewhere. You can never have a reaction that only gains or only gives off. That's just half a reaction, right? So let's look at chlorine. What is chlorine? Chlorine started out as Cl2 on this side. What is the charge of the chlorine on the other side? Now it's chloride. And in chloride, it is Cl minus, right? Now first, let's balance the atoms. There must be two. You can't have atoms leaving, right? And now we must balance charges. Charge must be conserved. If I have Cl2 and there's 2 Cl minus, where must the electrons go? In front or at the back? In front. 2 electrons over there. So now the total charge on the left-hand side is 2 minus, and the total charge on the right-hand side is 2 minus. And this is now my redox half reaction. Right, my redox half reaction. And then we can say, okay, but they happen together. They happen at the same time. And now I just have to check. This one releases 2 electrons. That one uses 2 electrons. Perfect. So now this is my redox reaction. And now it's a reaction. It's not a half reaction. Because electrons are both given off and gained. And then you have them all together. Now, just remember, everything on the left-hand side of that arrow is what we put in. Keep them on the left-hand side. Everything on the right-hand side is what you get afterwards. It's the products. They must stay on the right-hand side. Right. Let's do the same thing now, but let's do it with aluminium and chlorine. Sorry, guys. Okay. Aluminium and chlorine. What will we get as products? Aluminium chloride. What does aluminium chloride look like? Aluminium chloride should be AlCl3. AlCl3. Okay, now, what you used to do, what you learned in grade 9, is to balance by inspection. It's by looking on the left-hand side and looking on the right-hand side. Right. So how did we balance this? We said 1 aluminium, 1 aluminium. That looks good. Right. But then we get to 2 chloride, 3 chloride. That does not look good. So how do I change it? I'm going to put a 3 in there and a 2 over there. Right. But the moment that I put it over there, then it also changed the aluminium. So I have to put it 2 in there. Now let's just check. 2 aluminium, 2 aluminium. 3 chlorine, 3 times 2, 6 chlorine. 2 times 3, 6 chlorine. Now it's balanced. That was balancing it by inspection. Looking on the left hand, looking on the right hand side. Right. But they can also ask you to balance something by using half reactions. So let's take this one. What is the half reactions over here? Now, aluminium starts without a charge. It's got a 0 charge, and it ends up with plus 3. Will it be gaining or losing electrons? Losing electrons. So this is my oxidation half reaction. It is the aluminium that is going to aluminium plus 3. How many electrons on which side? 3 electrons on the right-hand side. Total charge left, 0. Total charge on the right, 0. We've got conservation of charge. Then look at the chlorine. It's 0 over there. It's minus 1 over there. This is my redox half reaction. So you're starting out with Cl2 and you're ending up with Cl minus. Now, never mind the 3's and the 2's up there. Think about this reaction. 2 chlorine atoms. I have to have 2 chlorine atoms. You can't have atoms escaping or disintegrating or whatever. Atoms must stay the same. And now I have to put in the electrons. Which side, left or right? on the left-hand side, right? I have to put on the left-hand side. How many? 2. Every chlorine will take 1 to make a -1 charge, right? So now on the left-hand side, you've got a total charge of 2 minuses. And on the right-hand side, 2 minuses. So you know you're right, because you've got conservation of charge. Right, and now we want to put them together to get our redox reaction. Now, we've got a problem, because this one releases 3 electrons, and that one only gains 2. So how can I make this one happen in such a way that we've got equal amounts released and gained? I have to make the first one happen twice in the time that the second one happened 3 times. So I'm going to take 2 of these to produce 2 of those, and 2 times 3, 6 of those. Right. And the second one, I'm going to say, I'm going to let that happen 3 times. So 3 of these, 3 times 2 is 6 electrons, will give me 6 of those. So I multiplied all through by 3. So now I'm fine. I'm releasing 6 and I'm gaining 6. That's fine. So now I'm going to add them together for the redox. And what do I have to remember? Everything left of the arrow is what I put in. So keep them on the left-hand side. Everything on the right-hand side is what I get out. 2 aluminium plus 3 and 6 Cl minus. Right. Now this is the redox reaction. Now these are already without a charge. We can say they're molecular. They don't have charges. How can we put aluminium and chloride together? Aluminium, 1 aluminium will bind to how many chlorine? 3. Plus 3 and just minus. So every aluminium will take 3 of the chlorides. And we have 2 aluminium. So how many chlorides? 6. And can you so now see it's balanced? So this one we balance by inspection, by just looking on the left and the right-hand side. This one we balance by using half reactions, by getting the separate reactions and watching the electrons to see what's happening. It's nice. So it gives exactly the same answer, but it's a different method. Right, let's go on from there. Now, this was things that got ionic as really got charge. Yes. Yes. You don't have a specific question, you're just confused. Okay, let me go on, and we're going to do 2 or 3 more, and I think you'll get into this. So we are going to use the charges to work out what happened with the electrons. Now, sometimes when you look at charges, we are going to work with things that's not ionic. Right, we're going to work with things that are not ionic. Now, if you go to page, the first page that we're working on is page 44. 44. Now we are going to look at what happens if it's not an ionic thing. If it's not ionic, it's covalent. And covalent doesn't have charges, right? But we want to know what happens with electrons. So with covalent things, we're going to work out what would the charge have been, sort of. We're saying, what is the oxidation number? That is, what would the charge have been? If something is ionic, then the charge and the oxidation number is the same thing, right? But if it's covalent, then it is sort of, what would the charge have been? And there's ways to work this out. Now, let's talk about oxidation. If you have oxidation, let's say you have copper. If copper reacts to give off 2 electrons, this is oxidation because it is releasing electrons. Everyone happy with that? Okay, but we don't always want to think about electrons. Just look at the charge. What is happening to my oxidation number? What's actually happening to my oxidation number? It's going from 0, because it's got no charge over there, to +2. If my oxidation number increases, then I know that substance is oxidizing. Because you are releasing what? Negative things. Therefore, my oxidation number becomes more positive. So having an oxidation number is a nice way to see if this is oxidation or reduction without even thinking about electrons. So first thing we're going to do is we're going to assign oxidation numbers. And there's a few rules. Now, most of the textbooks have got the few rules, and then there's a lot of exceptions. But the exceptions you see once in a blue moon, right? Usually it's just the basic rules. So let's start off with the basic rules. We can talk about the exceptions, but what's the basic rules? If you've got a pure element, that will take 0. Say, for instance, you've got sodium. We will say the oxidation number of that sodium is 0. Right. How about Cl2? Okay, I can make it bigger for you. Like this. Okay, right. How about the chlorine? It's a pure element. It's not bonded to something else. So it will also take a 0, right? So it doesn't matter if it's one or more bonded together. It's just one element, then it's a pure substance. It takes a 0. Right, but then if it is in a compound, how about hydrogen? Hydrogen in a compound, you 99% of the time are going to use hydrogen as the +1. Right. Oxygen will be -2. Something is in group 1 is going to be +1, and something that's in group 2 is going to be +2. Right. Now this is not new. You've done it last year, so let's see how well you remember that. So let's look at this first one. I'm asking you to determine the oxidation number. Let's see if I can even make it bigger. Right. So I'm even making it bigger. There it is. Okay. So I'm asking you to determine the oxidation number of the indicated elements in the following compounds. Now I'm looking at H2SO4. Now, hydrogen is in a compound, therefore this hydrogen will be +1. And now I want to ask you, at the top, write what is the oxidation number for one atom, and at the bottom below that we're going to say what are they together. Right. So one hydrogen is a +1. Together that will be +2. Every oxygen is a -2. So altogether 4 of them will give you -8. So where are we? We've got -6 down here. Does it have a small number there in the corner? No, it's H2SO4, nothing. Hey? So it doesn't have a charge. Altogether the charges must add to be 0. So I've already got -6. So the sulfur has got to be +6. To make it come to 0. Next one. We've got, what is Pb? Lead. I've got lead oxide. Now, every single oxygen is a -2. So together they will be -4. So what should the oxidation number of the lead be? +4. Right, we get to the iron oxide. Every oxygen is a -2, so this part of the compound is -6. What should the total be? 0. So these two should be +6. So what is every iron atom? Every iron atom will be a +3. Next one. Potassium. What do you know about potassium? Periodic table. Potassium is in group 1. So potassium is +1. That means the 2 potassiums together will be a +2. Right. Oxygen, -2. 7 of them will give you -14. So where am I at? -12. So the 2 chromes should together be +12s. So every chrome atom is a +6. Right, next one. Every oxygen is -2. 4 of them together will give me -8. But this time, the whole thing together has got a charge of -2. So instead of being +8 and making 0, what must the sulfur be? Sulfur must only be +6, because you have to have 2 of the minus left over. Eh? 2 of the minus must not be cancelled out. Right, next one. Now here I have something different. I don't have the iron charge. I'm looking for that. but I also don't have the chrome. So I've got a problem. But fortunately, you know your tables of ions by heart. What's that ion called? It's the dichromate ion. For those who can't remember, just turn quickly back to the second large page. The dichromate. What do we know about the dichromate? Altogether, this is -2. So that ion must be a +2. So that's a different way to do it, a different method. Right. So with ionic things, you are going to use your table of ions. Right, next one, vanadium pentoxide. That's actually one of the catalysts that we use in the contact process for fertilizer. Right, every hydrogen is -2. 5 of them together, -10. So the 2 vanadium must be +10 altogether. So every vanadium is a +5. Right, we're going to the right-hand side. Hydrogen is +1. Oxygen, -2. So we've got a +1 over there. We've got -6 over there for the total. So we're looking at -5. So that chlorine should be a +5. Next one, we're looking at iron sulfate. Sulfite, SO3. If you're looking at sulfite, I'm looking for the sulfur, but now I don't have the iron charge. So first, tell me, if I look at the sulfite, what will be the charge of the sulfite? -2. So that ion should be a +2. And then we look at them separately. Every oxygen is a -2, so this gives me -6. So where do I end up? -4. So that sulfur should be a +4. Next one. Oxygen is -2. 2 of them together will give you -4. That sulfur should be a +4. Right, and then there's 4 more for you to do. +1, oxygen -2, so altogether that 3 will be -6. So we're up to -5, so that nitrogen is a +5. Now, maybe some of you have problems with this, because if you think about something like sulfur, what is the charge of sulfur usually? Where do you find sulfur on the periodic table? You find sulfur over there, right? So sulfur has got 6 valence electrons because it's in group 6. What is the shortest route to noble gas structure? To gain 2 electrons, right? So you will often have sulfur with a -2 charge. Then you call it sulfide. But you can also have the sulfur giving all 6 off to have the previous energy level filled. So then it will be +6 because it's giving off 6, right? And then something else. If it can't give off all 6, remember up to there, this is the s orbital, and then you're starting filling up the p orbital. So if there's not enough other atoms around to take all 6, then maybe there's at least one that can take 4. So then you've got a filled s orbital. So it's sort of second best. It's not really a filled outer level, but it's just a full sub-level. So what you have to remember is it does not always do the shortcut thing. So there will be different charges. Don't be upset by the fact that you've now got chlorine with a +5, or you've got sulfur with a +6. That may not be your usual charge, but that is the charge, or the oxidation number at this time. Right, let's look at the second one, third last one. Sodium, what do you know about sodium? Sodium's group 1. So one of them will be +1, 2 of them will be +2. Every oxygen is a -2. There you've got -6. +2 -6 gives you -4, so that sulfur should be +4. Right, here. If you look at this one, hydrogen is +1, oxygen is -2, so what is that chlorine? +1. What do we know about chlorine? What does chlorine usually do? -1. Where do you find chlorine? You find chlorine over there, right? Chlorine is the group 7. So usually it wants to gain an electron, right? It wants to gain an electron to get noble structure. When you're looking at elements and you're looking at people, do you know what's the difference between elements and people? With people, everything is about being a millionaire. Right. Everything is about being a millionaire. So everyone is doing things to become a millionaire, but people are different, right? You've got people who will, right, we'll see what you will do to be a millionaire. Some people will really go to extreme lengths. Some people will kill someone to become a millionaire. Some people will just work very hard to be a millionaire. Some people will try to be a millionaire, but it's not that important, right? And then you've got teachers at the other end of the spectrum. They don't mind about being a millionaire. They just love what they do, right? So with people, it's all about being a millionaire. What is the all about for elements? What does elements want to do? They want to have noble gas structure, right? They're always fighting for noble gas structure. That's what they want to do. That's stable. So just as people are different, different elements are also different. Some of them will fight very hard to get noble gas structure. Some of them will try to get noble structure, and some won't even mind. So we'll see about that soon, right? So it's all about getting noble gas structure. So here, chlorine usually wants to gain an electron to get to noble gas structure. So what do you think about a chlorine that is +1? That is a very upset chlorine, right? It actually wanted to gain one in order to become a noble gas structure. And what did someone do? Someone even removed the single one that it had, right? So what is this chlorine going to do? It is going to look for electrons. It is going to try to take up electrons. It's going to try to reduce, right? So it will be very good at taking electrons from other substances. So we use it. We use it when we have bleach, for instance. In bleach, you have the chlorine with the +1. And it's looking for electrons. And it comes to your clothes and it says, oh, red, I know you like your electrons, but give to me. Okay. And what happens to the red? It falls apart and becomes white. So it's bleached, right? You put it into your swimming pool. What happens when you put it into your swimming pool? It goes to the algae, right? And you say, okay, I need your electrons more than you do. Give, right? And what happens to the algae? They die. And you've got a nice swimming pool, right? So sometimes we want the chlorine upset, right? We want the chlorine upset. So the oxidation number is very important. It tells me in what state is that atom. Is that atom already happy and not looking to react? Or is it reactive? This one is reactive, right? Now, how about copper? Now, here we had the other way once again. You had to know that carbonate atom, iron is a -2, and therefore that copper is a +2. Right. So this was assigning oxidation numbers. Now on the next page, let's look at this. If you look at oxidation, we now said it's something like copper going to copper plus 2 electrons. It is loss of electrons. But in future, we're going to take a shortcut. We're not even going to talk about the electrons. We're just going to talk about the oxidation number. What happened to the oxidation number over there? If you lose negatives, then my oxidation number increases. It becomes more positive, right? So what we're going to do is we're going to use that. Now let's start with this example over here. You've got copper over here. It's not bonded to something. It's a pure substance. What's the oxidation number? 0, right? And copper on the other side, it is bonded to a sulfate. So what is the copper on that side? Plus 2. So this copper is going from 0 to plus 2. Don't think about electrons. Think about oxidation number. What's happening to my oxidation number? It is increasing. So immediately tells me my copper is undergoing oxidation. It is oxidizing. And how about this one? Now the hydrogen over there has got a plus 1. How about over there? Also plus 1. So the hydrogen did not change. Right. Look at the oxygen. Minus 2, minus 2, minus 2, minus 2. It did not change. Right. Now look at the sulfur. Sulfur on this side, plus 6. Sulfur on that side, plus 4. What happened to the oxidation number? It reduced. So we're saying sulfuric acid is reducing. It's undergoing reduction. Right. Now actually I looked just at the sulfur. But remember, if sulfur wasn't on its own, it would not have had a charge of plus 6. And it would not have done the same reaction. So who's reducing? Not the sulfur, the whole H2SO4 altogether, right? Okay, let's do that. Now the first one there, I've got a question. Identify the oxidation agent. Now we haven't talked about agent yet. What is an agent? It's something that helps someone else to do something. If you want to sell your house, you ask an agent to help you, right? Your real estate agent. If in chemistry you want to dry something, you add a dehydration agent. So an agent is something that does not do it himself. That agent does not sell his own house. He sells someone else's house, right? So if you have an oxidizing agent, it is something that will help the other substance to oxidize. How? By reducing. Right. So the oxidizing agent will reduce, it will take up electrons so that someone else can give it off. So in this one, the one that oxidizes is my reducing agent because it helps the other one to reduce. Now let's look at this one. What is the oxidation number of hydrogen on the left-hand side? 0. Nice. Chlorine on the right and on the left-hand side, 0 as well. Hydrogen, it's in a compound, plus 1. So that chlorine over there is a minus 1. It's more or less a happy chlorine, hey? How about the hydrogen? It's going from 0 to plus 1. What's happening to the oxidation number? Oxidation number is increasing. So what is the hydrogen doing? It is oxidizing, and therefore it is the reducing agent. Chlorine, over there it's 0, over there it's minus 1. What's happening to the oxidation number? It's decreasing, it's reducing. So chlorine is reducing and it is the oxidizing agent. Next one, sodium. It's on its own. It's a pure substance. Therefore, it takes 0. Over here, hydrogen in a compound, plus 1. Oxygen in a compound, minus 2. Sodium on this side, it's in a bond. Sodium is a group 1. What do we know about group 1? Plus 1. Oxygen, minus 2. Hydrogen, plus 1. That hydrogen at the end, pure substance, 0. Right, so let's look at the sodium. Sodium goes from 0 to +1. 0 to +1, oxidation number increases. This one is oxidizing. It is the reducing agent. Right. Now, you can't look at the oxygen. The oxygen is -2 and -2. It's not changing. So we're going to look at the hydrogen. Now, from there to there, it's +1 and +1. That's not changing, right? But from there to there, it is changing. What's happening to the oxidation number? It's decreasing. It's reducing. So the water reduces, and it is the oxidizing agent. Next one, you've got zinc. It's on its own, therefore it's got a 0 oxidation number. Copper bonded to 2 chloride atoms. What do we know about a chloride atom? Chloride is a -1, so altogether they are -2, so that copper is a +2. On the other side, chloride is -1, it makes that -2, that zinc is a +2. That copper, 0. Right, so the zinc is going from 0 to +2. What's happening to the oxidation number? Increasing. Okay, so zinc is oxidizing. It is the reducing agent. At this one, now, what do we call something that is not changing charge? It is a spectator ion, right? If you look at the chlorine over there, it's minus. If you look at the chlorine over there, it's minus. It's just sitting by. It's not doing anything, right? It's a spectator ion. So the chlorine is a spectator ion. Look at the copper. What's happening to the copper? It's starting with +2, and it ends up as 0. So the oxidation number is reducing, telling me that copper chloride reduces. It is the oxidizing agent. Right. You may not say copper reduce. You may even say copper 2+ reduce. You may not say copper reduce, because copper on its own would not have done this. Copper on its own would have had a 0 charge. It would have reacted differently. You have to say copper chloride, or at least copper 2+ is reducing. It is the oxidizing agent. Right, last one there. Every hydrogen will be a +1, so altogether they will be +3, making that nitrogen into a -3. Oxygen on its own, 0. Oxygen on its own, -2, therefore that nitrogen will be a +2. Hydrogen +1, oxygen -2. Okay, let's look at the nitrogen. It goes from -3 to +1. The oxidation number increases. Therefore we say ammonia is oxidizing, and that is the reducing agent. How about oxygen? Well, it doesn't matter if you go to there or to there. It's going from 0 to -2. So what's happening to the oxidation number? It's decreasing. It is reducing, telling you that oxygen reduces, and it is the oxidizing agent. Right. It will help the other one to oxidize. Okay. Quickly, on the next page. We've talked about this. I want to ask you, are the following reactions redox reactions? Are the following reactions redox reactions? Tell me, is the first one a redox reaction? A redox reaction is one where there is electron transfer, and I will see it because there will be a change in oxidation number. There must be a change in oxidation number to show me that there is electron transfer. So if you look at this first one, is that a redox reaction? Yes. You don't have to check every single one. Just check one. If there's one that changes, then it's fine. Can you see the lead? Out there it would have a 0. And in there it would have something else. And that is good enough to tell me there's something changing oxidation number, there's electron transfer. How about the next one? Is that a redox reaction? No, that is actually ion exchange. Right, the magnesium is still +2 on that side. The hydrogen is still +1 on that side. Nothing changed charge. It just swaps places. How about the third one? Is that a redox reaction? Yes, the easiest way is to look at the oxygen. There it's 0 and there it's not 0. Okay, it's a redox reaction. Okay, now we're going to use half reactions to balance the following redox reactions. So let's look at this one. What is the charge of the aluminium on this side? It's a 0. It's a pure substance. How about the silver? It's bonded to a nitrate. Now, you'll see the nitrate over there and you'll see the nitrate over there. So the nitrate is not changing. What do we call the nitrate? Spectator ion. Right, so we're looking at the silver. What is the silver ion on this side? It will be +1 because nitrate is -1. So that silver is a +1. See if we can make it a little bit bigger. Better. Right. How about the aluminium on the other side? What is the charge of the oxidation number of that aluminium? Every nitrate is a -1, so that aluminium is +3. That's what we would expect because it's in group free. And that silver is on its own. So if you look at the aluminium, what's it doing? The oxidation number is increasing, so the aluminium is oxidizing. So if we looked at the oxidation half reaction, that will be the aluminium going to aluminium +3. So it's going from 0 to +3, telling me it's oxidizing. So I'm writing the half reaction by saying aluminium goes to Alum +3. Which side should the electrons go, on the left or on the right? On the right-hand side. Why? Because I have conservation of charge. Total charge on the left-hand side must be the same as the total charge on the right-hand side. That's fine. Reduction. Now, if you look at the silver, it's going from +1 to 0. So what's happening to the oxidation number? Decreasing, reducing. So this is a reduction. So you start with Ag plus, and you end up with Ag without a charge. So which side should the electrons go? Left-hand side. How many? Just 1. Okay. So this is my half reactions. Right. Now, what do I know? Electrons must be conserved. Charge must be conserved. So you can't have releasing 3 and only using 1. Where's the other 2 going? Huh? Some mischief somewhere. I don't know. Okay. So we're never going to do that. We're always going to release and gain the same number. So what do we have to do here? We have to let the second one happen 3 times for every single time that the first one happens. So you have 3 of these, taking 3 electrons to produce 3 of those. And then altogether, if we get the redox reaction, that will be aluminium +3 Ag plus, everything left of the arrow stays on the left because that's what I put in. And that will give aluminium +3 and 3 silver atoms, and that stays on the right because it's produced. Now that is ionic because it's got charges, it's got ions. So sometimes they might ask you to make it molecular. So now we don't want ions. So what am I going to do is just put back my spectator ions. So aluminium is fine, no charge, right? But how about the silver? How can I get rid of that positive charge? By putting my spectator nitrate back. So I'm putting nitrate back in there. Silver is +1, nitrate is -1, so it looks like that. It's fine. But I had 3 silver ions, and therefore, what am I adding on the left-hand side? 3 NO3 minuses are new to my equation on this side. Okay, let's go on to the other side. Aluminium. What do we know about aluminium? +3. So if I need nitrates for that, how many nitrates? 3. So what am I adding on that side? 3 nitrates. Wonderful. What I put on in the left-hand side, I must put in at the right-hand side. And the silver is already without a charge. Right, so the next one is for you to do. Right. Let's see how you feel with this next one. Yes. The very last one. Okay, are you all right with the ionic one? Okay, now let's just go back slowly. Do you know how to get the oxidation one? From the oxidation numbers, right? And do you know how to get the reduction one? From the oxidation numbers. And then you have to get the electrons to be the same. Happy there? So then you just add everything on the left-hand side stays left, everything on the right-hand side stays. But now you've got things with charges. So it is ionic. So if they want to, they can ask you to put back the spectator ions so that there's no charges anymore. What was my spectator ion over there? It was nitrates. So let's put back nitrates wherever we need them. So we're starting off on this side. The aluminium is already neutral. So just leave it. But then you get to the silver. So how do I make it to be neutral? I put nitrate in there. How many? Silver is +1 and nitrate is -1, so 1 to 1. But I've got free silver atoms, so I have to make free of that silver nitrates. So what do I add here that was not in the previous one? 3 nitrate ions. But whatever I put in on the left-hand side, I must put in on the right-hand side, because up to there it was balanced. So I just can't go put in substance on the left-hand side and not on the right. I must do the same. But fortunately, that aluminium is 3+, so it will take 3 nitrates to make it neutral. And then you end up with everything neutral. And I've added the same amount of nitrates on both sides. So that is my molecular formula. Right. No ions anymore. Okay. See how you can do the second one. For some and for some not. Okay, let's do this one slowly. Guys, this is actually a really grade 10 and grade 11 background, but we have to make your background right. So let's look at the next one. Now, I want to have the oxidation half reaction, so let's start with this one, nitrate. What do I know about a single nitrate? Nitrate is a altogether NO3 minus, right? So 1 nitrate is a -1. What will 3 nitrates be? -3. So I'm actually starting off with an ion with a +3 charge, right? That thing, it's on its own, so that is 0. Then I'm going to zinc on this side. What do I know about nitrate? Is -1. There's 2 nitrates, so this is -2, so that zinc is a +2. And that ion is on its own, so that's a 0. Right. So let's look at the ion. What's happening to the ion? Ion is going from +3 on this side to 0 on that side. What's happening to the oxidation number of ion? It is decreasing, it is reducing. So ion 3+ will be my reduction one, hey? Because it's being reduced. And now I look at the zinc. What's happening to the zinc? Zinc is going from 0 to +1. What's happening with that oxidation number? Increasing. From 0 to +2. So it is increasing. And if it increases, it tells me the zinc is the one that is oxidizing. Right. That's how I know which one is which half reaction. Right. So let's start with the zinc. Zinc is starting out as 0 on this side, and it is ending up as zinc +2 on that side. How many electrons on which side? 2 on the right-hand side. Good. 2 on the right-hand side. So there's my half reaction. So you don't look at the table yet. You write this by looking at the zinc. Next one. We're looking at the iron. Iron on this side, +3. Iron on that side, 0. Which side, how many electrons? This side, 3 electrons. Right. So now, the separate reactions are balanced. And now what do we have to do? We have to look at the electrons. You can't add extras. We have to use what we have. This one is producing 2. That one is using 3. How can I make it to be the same? I'm going to multiply the top one by 3. 3 zinc, give you 3 of those and 6 of those. Multiply it straight through with 3. And at the bottom, multiply by 2. So now I have 6 released and 6 gained, and that is fine. Then to get the redox reaction, I'm going to add them together. 3 zinc plus 2 Fe3+, that's everything on the left-hand side of the arrow, is the same as 3 Zn2+ plus 2 Fe, that is all on the right-hand side. So this is already my redox reaction, and usually you can leave it like that, ionic. But just for now, for practice, let's put the spectator ions back. So the zinc is already neutral. Don't fuss. It's already neutral. Look at the iron. If iron is +3, it will bind to 3 nitrogen. Everyone happy? But we had 2 ions, so don't make the ions less. We already had 2. So how many nitrate ions am I adding on the left-hand side? 6 nitrate ions that I put in here. So remember, we have to do the same on the other side. So there we have zinc. And zinc has got a +2 charge. How many nitrates will bind to a zinc? 2. Because every nitrate is a minus, we need 2 minuses for the 2 pluses. We're fine. And now I had 3 zinc. So how many nitrates did I use here? 6 NO3 negatives. And that's wonderful, because I have to put on the left and the right-hand side the same amount, 2 Fe. So there's my redox reaction with spectator ions. Yes? Oh, thanks. Is it better? Are you starting to get there? Nice. Okay, so now we've finished with grade 11. May we go on with grade 12? Right. So let's go on with grade 12. Come on, guys. Seems to me some of you think this was new. This was not supposed to be new, huh? That was grade 11. Let's go on to matric. Now, if you turn the page, you come to a little one like this. Turn the page, and you come to that small pictures that look like this. Now, if you look at this, what I'm telling you is I take a small piece of zinc. That's a piece of metal, right? Hard, shiny metal. Put it into a solution of copper sulfate. Can any of you tell me what copper sulfate looks like? What does copper sulfate look like? It is blue, right? It is the one that is cheap enough for most schools to afford. You can buy it at the Dis-Chem or wherever. It's blue, right? So it's nice to use in demonstration. So this is bright blue, and you put your little piece of zinc in there. And now I'm asking you, will the zinc react? Will there be a reaction? Now, here we have zinc and we have copper. What is important about the zinc is a piece of metal, so it's got no charge, right? If it is a solid, I can tell you it's just the metal, it's got no charge. And I'm adding that to the copper. So the copper over there is actually a copper 2+. Can you see that? It's copper 2+. And this is one of the most important things that you have to know before we get to cells. If something doesn't have a charge, it can't dissolve, right? It can't dissolve. If something doesn't have a charge, it's either a piece of metal that we put in, or it's a precipitate that forms. Something that doesn't have a charge is not in solution, right? And if you have something with a charge, it means that one will go into solution. Remember, water is a polar substance, and therefore polar things will dissolve well in water. So if it's got a charge, you know that is in solution. So if I just show you this without the picture, you should know it is a piece of zinc in a copper solution. Is that right? Now tell me, does things like zinc, does it like to be like that, or does it prefer to be 2+? 2+ being a millionaire. Hey? So both the zinc and the copper would like to be 2+, because that is noble gas structure. That is being a millionaire in atom terms. So they both want to, but it can't happen, because this zinc has got 2 electrons, and it can't put it into the dustbin. It has to be somewhere. So the only way that the zinc can get noble gas structure is the zinc gives it to copper. Right. Now, I always say it's like when you have the electrons, you're sitting at home and watching the babies, right? You have to sit at home and do the babysitting. If you can give the electrons to someone else, then you are free to go and to the movies, right? Because then it is dissolving. It can go away, right? What does the zinc want to be? Zinc or zinc 2+? It wants to be zinc 2+ to go into solution, to go to the movies, right? So it prefers to be with a charge, right? Not sitting at home. So if you've got the zinc 2+, without a charge, it means that's got electrons that it doesn't want. How about this copper? Is it happy? Yes, it's got noble gas structure. It's dissolved. It can go wherever it wants to, right? So now they are in competition, and the question is, who is fighting hard for noble gas structure? The zinc has got noble gas structure. The copper's got noble gas structure. The zinc doesn't have. Who's fighting harder? Do you know? I don't know. Turn back. Turn back. You definitely don't know, but this is where the table comes in. Right. Now, I know it's the first time you see this table. This table that we call, come on guys, give me a chance. Standard electrode potential, right? This table is my way to know who's fighting harder. If you look at this, it's half reactions. Now, it's written. Now, actually, I just have, before I take you to that one, just look quickly at your orange paper. On your orange information sheet, you will see there's 2 tables, right? There's 2 tables. Now, there's a little bit history to this. Every province used to have its own final exam. And then we decided we should have one final exam. So everyone had to write the same exam. But some provinces used the one and some provinces used the other. So instead of deciding which one to use, which I would have preferred, they decided, okay, we put both in, because it doesn't matter which one you use, right? So you can use any one. For today, I'm going to use the one with the lithium there at the top, the one on the right-hand side. That's the one in your books as well, right? But it doesn't matter which one you use. What is the difference between the 2? Look at the 2 and tell me what's the difference. The one is just upside down, right? So the thing that you must take away today is you may never say it is higher or lower on my table. Because your table might be like that, but your next door neighbor will use the other one. So for what's higher on yours will be lower on his. Right. So may you use the word up or down or lower or higher on your table? No. So if we can't use higher or lower, what should we say? Now, if you go back to your table, they have wording that is horrible. You can't understand it. But look at the side there. Do you say increasing, reducing ability? Okay, I would like to substitute that and say the stronger reducing agent to the top. Do you see that arrow? It says increasing, reducing ability. It's an increasing ability to reduce the other one. And that means it's a stronger reducing agent. So on your table, on the right-hand side at the top, there you will find the stronger reducing agents up to the top. And on the left-hand side, increasing oxidizing ability, which means you find the stronger oxidation agent there, down at the bottom. Right. So you have the stronger reducing agent at the top, and this one tells you you have the stronger oxidizing agent there at the bottom. So this table is going to tell me who's fighting harder. Right. And it is written in the way that from left to right, is it a redox reaction, reduction or an oxidation from left to right? Left to right is gaining electrons. That's a reduction, right? The guy who is reducing, the substance that is reducing is the oxidizing agent. So the things on the left-hand side, that's an oxidizing agent, and it reacts to the right. It reduces. And the reducing agent is on the right-hand side. It reacts to the left. It is oxidizing. So going to that side will be oxidizing. Going to that side will be reducing. Right, now we look at this table. They said the stronger reducing agent on this table, it is higher. I may not talk about higher. So go and watch the values of the volts. We call it the E0 values of this half reaction. So this half reaction has got a specific E0 value. What can you see about stronger reducing agents? If it's stronger, it is a more negative E0 value, right? So you will never say higher. What will you say? It's got a more negative E0 value. So a stronger reducing agent has got the more negative E0 value. It's got a more negative E0 value. So now they can give you strange things that are not even on the table. They can tell you, I've got A plus, which reacts with an electron to give you A, and I've got B plus 2 electrons gives you B, and the voltages are minus 1.14 and minus 1.30 volts. Which is the stronger reducing agent? The stronger reducing agent is the one with the more negative E0 value. So immediately this one has got a more negative E0 value. So this one is the stronger. So B will be the stronger reducing agent. So you may never talk about top or bottom. You talk about more negative E0 value. That makes it a stronger reducing agent. Right. So now back to our problem. What was our problem? Our problem was we had zinc and we had copper. And the zinc was in the neutral state, it was solid, and the copper was the +2 that was in solution. Who was the happy one, the copper or the zinc? The copper. It's got noble gas structure. It can go into solution, right? So the copper was the happy one. And now we go back to our table and we look at copper and zinc. Where do we find copper and zinc on this one? Zinc over there. Now, there's a lot of coppers. For copper, I want you to use the one that has got copper 2+ on that side and plain copper on this side. Can you see them? Zinc and copper. Which is the stronger reducing agent? The zinc. It's got the more negative value. Remember, stronger reducing agent. On this table, it's higher, but you shouldn't say higher. You should say it's got the more negative E0 value. Right. So, if you go back to that, we're going to say zinc is the stronger reducing agent because it is got the more negative E0 value. Right. So what does that tell you? Stronger reducing agent will fight harder to oxidize. Remember, reducing agent, oxidize. So who's fighting harder to oxidize? This one. So the zinc is stronger. It will give electrons to the copper. It would tell it, take the electrons. You babysitting this evening. Right. Take the electrons. So it's giving off the electrons. Right. It wants to go to noble gas structures. It's giving off the electrons, so the zinc will end up as what? Zinc 2+. It's given the electrons to the copper. And what happens to the poor copper? It's receiving the 2 electrons. It's now copper without a charge. What does that mean? It's the piece of metal, or it's a precipitate. It's just sitting there, right? No dissolving and going anywhere. It's sitting there. So if you look at this one, the zinc is the stronger reducing agent. So what's happened to the copper? It's going from +2 to 0. It's reducing. Why is it reducing? Because the zinc is the stronger reducing agent. It makes the copper reduce. Does that make sense? So if they ask you, is this spontaneous? The first thing to go to the table to see who's fighting harder to be in the oxidized state. Zinc is the one that is fighting hardest. Zinc has got the more negative E0 value, so it's this stronger reducing agent. It will tell the copper to take those 2 electrons. So what will I observe in this reaction? Now remember, we started off with the zinc. The zinc was a solid, right? We started off with a piece of zinc. In what form does the zinc end? It ends up in 2+. And what does 2+ tell you? It means it will dissolve. It will go into solution. So what will happen to this piece of zinc? It will become smaller and smaller and smaller. Why? It's giving off electrons. Is that a problem? No, electrons are so small. That doesn't make it smaller. What makes it smaller? The zinc becomes zinc 2+, and then it goes into solution. And now there's a little hole where that zinc used to be. Right. So the zinc is the one fighting harder to be oxidized. It's telling the copper, take this electrons. And then the zinc is 2+, and it's free to go into solution. Right. So the zinc is the stronger reducing agent. What happens to the copper? Now the copper was in solution. It was drifting around. Then it made the mistake of bumping into that zinc, which is stronger. And the zinc gave the electrons to the copper. And what happens to the copper? It ends up without a charge. If it doesn't have a charge, what does it mean? Sitting down, right? It's a precipitate, right? It's a precipitate. So what will I see? I will see the zinc getting smaller. That's the first thing I will see. And what will I see? I will see this copper solution. What's the color of copper solution? Blue. What will happen to the blue? It will become lighter and lighter because my copper ions are being used, right? And what will I see? I will see a brownish precipitate forming there. Because if it doesn't have a charge, it is in the metal, it's just the atom. It will sit there. It will either be a piece of metal or it will be a precipitate. Right, so this is what happens. So with the first one, since zinc is the stronger reducing agent, it will oxidize. It will give off 2 electrons. Right. If you do it the other way and you put a small piece of copper into a zinc solution, you will say, The zinc is actually the stronger one, and it's already oxidized. So then there's no reaction, right? Then it will stay the same. So if the stronger one is not yet oxidized, it's not yet winning, it will react to win. If the copper is the weaker one, it can't make the zinc take the electrons. Sorry, copper is the weaker, sorry, I see you've got Afrikaans there. It's the weaker reducing agent. And if it is the weaker reducing agent, it cannot, that copper cannot reduce the zinc 2+. So it's all about who's fighting harder, right? Who's fighting harder to have noble gas structure. So let's go up to the top there. First thing I ask you, if you look at the table, go look at the table and see who is the better reducing agent. Is copper or magnesium? Sorry for that A there, just MG, typing error there. Is copper or is magnesium the better reducing agent? Where do you find copper? Where do you find magnesium? Magnesium over there, copper down there. Who is the stronger reducing agent? Magnesium, magnesium. And if they ask me for a reason, what will I say? It's got a more negative E0 value. It's got a more negative E0 value. Right. Now the next one, they ask you, you've got magnesium +2 and you've got nitrate, nickel +2. Who is the better oxidizing agent? So let's go see, magnesium and nickel. So magnesium 2+ over there, nickel 2+ over there. What do we know about oxidizing agents? Oxidizing agent, it's the other way around. Hey, so this one will be nickel 2+. Right, next question. Which substance will more readily gain electrons? Now give me a scientific word for gain electrons. Reduce. So the question is actually, which substance will reduce more readily? And the one that reduces more readily is the stronger oxidizing agent. The stronger the oxidizing agent, the more readily it will reduce, the more readily it will gain electrons. So now we have to go back to the table. We're looking for the stronger oxidizing agent, lead and zinc. Lead and zinc. Lead Pb over there, zinc Zn over there. Who is the stronger oxidizing agent? The lead. Next one, magnesium will more readily lose electrons. Give me a scientific word for lose electrons. Oxidize. If you more readily oxidize, it means you are the stronger reducing agent. So then we're going, magnesium and zinc. Where do you have magnesium and zinc? We've seen them already. Magnesium over there and zinc over there. Who's the stronger reducing agent? Magnesium. Because it's got the more negative E0 value. Right. So if you read gain electrons, immediately translate to reduce. Electrons gain is reduce. Who will more readily reduce? The one that is the stronger oxidizing agent. Right. So it's having your wording correct. Everyone happy? Okay, now let's see. The following reactions will occur spontaneously. True and false. True and false. We're not going to do all the explaining. Just leave the explaining. Just say if it's true or false. Now think about this. You've got silver plus and you've got lead. And they're asking us, is this going to be a spontaneous reaction? So what do I have to do? I'm going to see where lead and silver is on the table. So lead over there. Silver over there. So what can I see from my table? Lead has got the more negative E0 value, so lead is the stronger reducing agent. So that is the stronger reducing agent because it's got more negative E0 value, and it means that will fight harder to oxidize, right? It will reduce the silver. So what will happen? Lead will give electrons to the silver, and silver go from +1 to 0. If something goes from +1 to 0, the oxidation number is reducing, right? So it is reducing. Why is it reducing? Because lead, being the stronger reducing agent, force it to reduce, right? The lead is telling that silver, here's the electrons, I'm stronger than you, take, right? And the silver doesn't have a choice. Right, so what we say here is lead is the stronger reducing agent, and therefore lead will reduce the Ag to Ag. Ag plus to Ag. Right, so lead is the stronger reducing agent, and therefore it will be able to reduce the other guy. How about the next one? So this is a spontaneous reaction. Yes. Sorry? That means? Sorry? The lead is? Okay, go on with the next one. I'll go in here, there, and I'll talk about this afterwards. Sorry? Yes. Sorry, that was still meant true. Yes. Sorry, I heard 2 and I couldn't decide what's right. 2. Okay, so this one is definitely true because the stronger reducing agent is going to oxidize. It can reduce the other guy. So now let's see if the next one is true. You've got Ag plus and Fe. Now let's look at where's iron. Now, which iron? Careful, we're working with iron 2 plus. So where's the iron 2 plus? Iron 2 plus? 3 plus. There's the iron that goes with 2 plus. Right, so you've got that iron, and you've got silver, and silver is down there. Right. Which is the stronger reducing agent? Iron. So iron is the stronger reducing agent. So will there be a reaction? Yes, it's the stronger one and it's not yet winning. Right, but don't write that. What are you going to write? Fe is the stronger reducing agent, and therefore Fe will reduce Ag plus to Ag. Right. So this is also true. May I put a correct mark there? Okay. Right. Check the last one. Is that spontaneous or not? Right, true or false? Which is the stronger reducing agent? Zinc is the stronger reducing agent, but it is already oxidized. So it can't oxidize now. It's already oxidized. It's already winning. So here we're going to say lead is the weaker reducing agent, and therefore lead cannot reduce the Zn2 plus. Right. So this is definitely false. Right. Right, so now the question is, why do we spend such a lot of time on spontaneous and not spontaneous? Because we're going to look at two different types of cells. The one type of the cell is going to be galvanic cells, and the other type is going to be electrolytic cells. And galvanic cells is going to have spontaneous reactions. And the spontaneous reaction is going to give off electrical energy. We're going to get electrical energy from the galvanic cell. So you have a chemical reaction, so you have chemical energy, and it gives electrical energy. While when we're with electrolytic, it's going to be not spontaneous. We're going to put energy into the system. We're definitely not going to get there today. We're going to try to do a little bit of this. Everyone all right? Okay. So we are going to look at a galvanic cell. Now, a galvanic cell, if you look at the next page, that's sort of a summary of how I'm going to look at galvanic cells. Now, in a galvanic cell, they're going to tell you, for instance, I've got a standard magnesium zinc cell. How do I know what is spontaneous? I go to the table and I say, okay, I've got magnesium and I've got zinc. So the very first thing is you find the two equations on this sheet. Now I know it's those two that are going to react. And this reaction can either happen in that direction, or that direction. And now I want to know, okay, so what's going to happen? So the first thing to see is, who's the stronger reducing agent? Who's the stronger reducing agent here? It will be the magnesium, because it's got the more negative E0 value, right? Now this is a spontaneous reaction, so the stronger one will be winning. So the stronger reducing agent will be the reducing agent in this cell. And what do you know about the reducing agent? It's the one that has to oxidize, right? Now what is oxidation? It's loss of electrons. So this one must happen to that side, right? It's the stronger reducing agent. It should oxidize. Oxidize means it must happen in that direction because it must release electrons. Right. So the stronger reducing agent oxidize. It releases electrons. It must happen to that side. So if they're asking us the oxidation half reaction, it will be magnesium goes to magnesium 2 plus and 2 electrons. Right, so that's the stronger one. Now, if you're not the stronger one, then obviously you're the weaker one and you must lose. Eh? If you can't win, then you must lose. So this one obviously has to now go the opposite direction. Does it want to? No, it also wants to be in the noble gas structure. But not everyone can be noble gas, so okay. It has to do this, right. So what type of reaction does it do? It reduces. And therefore, the zinc 2 plus is my oxidizing agent. Right. It is undergoing reduction. So it is my oxidizing agent. It's happening to that side. So if they ask me, then I'm going to say zinc 2 plus 2 electrons go to zinc. That's my reduction half reaction. Right. So with all galvanic cells, you start by saying it's spontaneous. So the stronger one must win. So you go to your table and you see who is the stronger one and make it win. Right. So the stronger one is the one with the more negative E0 value. Therefore, it's the stronger reducing agent. It should oxidize. It should give off electrons, and you make it give off electrons. And then obviously the weaker one should take that electrons. Does it have a choice? No. Right. The stronger one is giving it to him. So it's happening in this direction. But one more thing. What is an anode? Anode is the word that we use for the electrode, the piece of metal where oxidation happens. Now remember, the vowels go together, right? You have oxidation always happen at the anode. So if they ask me what is the anode, it's going to be the magnesium. That's the metal where things are happening. Right. Now, let's go back and talk about spontaneous. We now said magnesium will react with zinc 2 plus. So you've got magnesium and you've got zinc 2 plus, right? And magnesium is the stronger reducing agent. So it will be giving electrons to the zinc. Now tell me, where is this happening? Is it happening on the bottom of the container? It is happening on the surface, right? When you have the zinc coming there, it will get the electrons for the magnesium, and it will, right there, it will react. So what's happening is the magnesium goes to magnesium 2 plus, and the zinc 2 plus takes 2 electrons, becomes zinc. So we said right on that surface, right? It will happen right on the surface. What will happen right on the surface? Magnesium give to the zinc. Now, what is nice is if we could take the magnesium over there, and we could take the zinc solution over there, and you put a wire between the magnesium and the zinc. Now, remember, the magnesium is the stronger reducing agent, right? It's the one that's better with giving off. So what's going to happen is this magnesium is going to send with the wire electrons to the zinc. It's the stronger one. So the electrons will be moving in the wire. And what do we call electrons? Charges moving in the wire. Electric current. So immediately I will go and put my cell in, my bulb in there, and I will have light, right? So what do we need to do? We need to put the oxidation, the giving off on one side, and the reduction, the gaining of electrons on another side. So what we actually do is we take the magnesium and we put it into a magnesium solution. Is this the solution or the magnesium that's actually reacting? It's the magnesium that reacts, right? And on the other side, we take the zinc and we put a small piece of zinc into a zinc solution. And now you have electrons going over. You have electrons going there. Electrons are moving there. Now, once the first electrons went over, that part is negative. Will the reaction continue? No. So now we have to complete. How do we complete this circuit? How do we make them go all around? We have to add a path. So what we do is we take a piece of glassware that is actually a pipe, a hollow pipe, right? We take a hollow pipe and we put in there a solution, right? And the solution we put in there is potassium nitrate. Why do we use potassium nitrate? Potassium is always soluble and nitrate is always soluble. So you don't get stuck with a lot of precipitate in there. They're both soluble. So you get on the one side the magnesium and on the other side the zinc. So what's happening? Electrons are traveling in the wire. If you look over here, magnesium is my stronger reducing agent. It's the one that is better with giving off. So it is sending electrons to the zinc solution on the other side. So you have the zinc 2 plus arriving there. And the zinc is, the electrons are given to the zinc 2 plus. What's going to happen to the zinc? It's going to become zinc without a charge. So what will you see on this side? The magnesium ends up as magnesium 2 plus. What's happening to that piece of metal? It's getting smaller and smaller and smaller. What's happening to the zinc on this side? It is going to get bigger, 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 because there's new zincs being deposited over there. So let's go back to this one. What's the first thing you do with a galvanic cell? Get your two reactions. Second thing, see who's stronger. The stronger one will be the more negative E0 value. It will be the stronger reducing agent. It will oxidize. In which direction is oxidation? It is towards giving off electrons, right? And then we take the weaker one. Now, obviously, it has to react the other way. If this one is giving off, this one has to take. It's the weaker one. It will be reacting in that way. So it will be reducing, and that makes my zinc 2 plus my oxidizing agent. Right. But what is a cathode? Cathode is the electrode, the piece of metal where reduction happens. So that can't be the zinc 2+. That must be zinc without a charge because it's got to be the electrode. Right. So we're up to there. We have oxidation, reduction, redox. And now I want to ask you, what is this? Come on. Something like that. It's music notation. Music notation, right. It's just a way of writing things down, but only the guys who know music can understand what's going on. Is that right? So the next thing we are going to do is we are going to learn cell notation, right? And cell notation is a way of writing things down that only the ones who know can understand. So let's look at cell notation. With cell notation, you have to have the oxidation half reaction will be in front, and the reduction half reaction should go to the back. Right. So it's actually what's happening in the oxidation beaker, and then there's a double line, and that double line actually represents your salt bridge. And then you get the other beaker where you have reduction. Right. And if you look at oxidation, oxidation is starting out with the magnesium and it's ending with the magnesium 2+, right? What do we know about magnesium? If it doesn't have a charge, it is solid, right? Then you get to magnesium 2+. If it's 2+, what does it tell you? It's a solution, right? It's a solution. Right, and now there's something new, 1 moles per cube decimeter. Now, if you go back to your table, at the top of the table, it said standard electrode potential. Why does it say standard electrode potential? Because it's only true at specific conditions, right? If you look at the conditions, on the summary page, down there, I put the conditions, standard conditions. It's down there. If you have standard conditions, then your table is true. So it might be not the stronger reducing agent at another temperature. It is only true at 25 degrees Celsius. It is only true when the concentrations are 1 mole per cube decimeters. So if they're at the top, they said standard cell, then obviously the concentration must be 1 mole per cube decimeters, right? So we're writing on the left-hand side oxidation, and oxidation is always the reducing agent that is producing something. So it always started off with the reducing agent, right? And then we get to reduction. Who's doing reduction? The oxidizing agent is doing the reduction, right? So this is the oxidizing agent, and that is the product formed during that reaction. Okay. And then one more new thing, and that is for the cell. Now, our table gave us E0 values, but that was just for that half of the reaction, right? So when you put the two together, what's going to do the EMF? The EMF of the cell, which is just your battery, right? You will get that, and that is on the information sheet. If you go to your information sheet, the orange ones, you will find the E0 of the cell is E0 of the cathode minus the E0 of the anode. So if you go to your table and you're working with magnesium, okay, table up there, the magnesium is my anode, so that is the E0 value of the anode. This is my cathode, so that is the E0 of the cathode. And you just substitute and get the answer. What is important with this answer is you need to have a positive, because it must be spontaneous. If you end up with a negative, you've done something wrong. You've chosen wrong or something. You have to end with a positive. Right, so let's recap quickly before we do a question. Galvanic cell, is it spontaneous or non-spontaneous? It's spontaneous. So the stronger one must win. So you look at your table to find the stronger reducing agent and make it oxidize. Right. And the weaker one must be the oxidizing agent. So it should reduce. It should take up electrons. And then you end up with that. And you can write the half reactions. We know how to add them. Right. And then we got to cell notation. Cell notation, you had to remember oxidation on the left-hand side, reduction on the right-hand side. You write it in the way that it occurs. Magnesium goes to magnesium 2+. Right. And the other one starts from this side. So you have zinc 2+. 2+ means solution. Goes to magnesium without a charge. That will be solid. Right. Okay, on the right-hand side, quickly see if you can answer question 1 to 4. The oxidizing agent. Where in my cell notation should I look for the oxidizing agent? The oxidizing agent is the one that is reducing. No. And the left-hand side is always oxidation, the right-hand side is reduction. So the oxidizing agent should be B plus 1. Hey? Okay. And you only know that because you know scientific cell notation. No. Right, next one. Which substance acts as the cathode? What do I know about the cathode? It's the metal where you find reduction. So it's the last part, which is the metal, B. Next one. Write down a balanced oxidation half reaction. Oxidation is the first part. So it should start out with A2 minus. It should end up as A without a charge. Which side should the electrons go? To the left or to the right? To the right. Total charge on the left-hand side is negative. Total charge on the right is also negative. Right. Then what will be observed at the anode? This is the anode. What will I see at the anode? Now, what happens at the anode is you start with something in solution, and what will happen to that something in solution? It's becoming solid. So what will I see? I will see a precipitate, right? I will see a forming of solid A. Right, I will see a precipitate. I will see A that is formed, solid, right? So you have four. Usually it is in more or less in powder form, so sometimes it fall down and lie at the bottom, sometimes it just cover the substance, but you will have a precipitate of A. Right, then there's another one. Now sometimes they give it to you in this way, telling you you've got a standard magnesium one. This time I'm easy on you. I'm telling you, I'm give you the cell notation to start with. Right. So see if you can answer those 7 questions, because that will tell you if you understand what's going on. Guys, let's stop quickly. Instead of that one, I'm going to ask you one other question. Let's start with one. I'm going to tell you I've got a standard magnesium, let's take magnesium tin cell. I've got a standard magnesium tin cell. Right. Now I'm going to just ask you, which substance will be the reducing agent? Which substance will be the reducing agent in a standard magnesium tin cell? So you have to use your table and decide if you've got a magnesium tin cell. Right. Can you tell me which is going to be the reducing agent in the cell? It will be the magnesium. Right. Can you write down for me the oxidation half reaction? That one's got the more negative, so it is the reducing agent. It will be oxidizing, which means it must give off electrons. It's happening to that side. Right. So the oxidation half reaction will be magnesium goes to magnesium 2 plus 2 electrons. So you've got 3 marks already. This is what they're going to ask you. Third question they're going to ask you is, which substance is the oxidizing agent in this reaction? Who's the oxidizing agent? Now, remember, this is the weaker one. It's happening to that side. And it will be the zinc, the tin 2 plus, not the tin, because that is the product of the reaction. It must be the tin 2 plus. There's your other mark. Right. Fourth question they're going to ask you is, give me the reduction half reaction. What is the reduction half reaction? It is zinc 2 plus 2 electrons, zinc tin 2 plus 2 electrons going to tin. That is 2 more marks that they're going to give you. Then they're going to ask you, okay, write me the redox reaction. What does the redox reaction look like? Now this is easy because 2 produced, 2 used, right? So that will just give you magnesium plus tin 2 plus 2 goes to tin and magnesium 2 plus. Everyone all right? Okay, redox reaction. Right, 6-1. Now this is for you to write. Write down your cell notation, please. Write down the cell notation. For this reaction, write down the cell notation. But let's make it count. Let's start with the cell notation. Now, what do we know about cell notation? We know there's going to be what happens in the oxidizing beaker, and then the double line is my salt bridge, and then what's happening in my reduction half reaction. Right. So let's start by the oxidation half reaction. The oxidation reaction will start with magnesium without a charge. What does it mean if its magnesium doesn't have a charge? It's solid. Right. And then we use a line to say, what is it going to form? What's it going to form? Now I look at this one. It's going to form magnesium 2 plus. And the moment that I have a charge, what do I know? This will be solution. Right. And if it's a standard magnesium tin cell, then I might even add 1 moles per cube decimeter. Sometimes they even leave that out on the memo. Right. But if it's standard, then it's 1. Right. Now I go to the reduction half reaction. reduction. It's happening from there to there. So you're starting off with tin 2 plus. What does the charge tell me? It's a solution, right, AQ, and if it's standard, it must be 1 moles per cube decimeter. And that, what is formed? Line to say, it is forming tin without a charge. What is tin without a charge? Solid, solid. Are you happy now? Good. Right, 6. The 7th thing I'm going to ask you is calculate the E0 value for my cell. What is the cell potential? Cell potential? It will be the E0 of the cathode minus the E0 of the anode. Right. Which is the cathode? Now, where oxidation occurs, that is the anode, right? So there, where reduction occurs, that is my cathode. So that will be minus 0,14 minus 2,37. Minus minus is actually plus. And you will end up with 2,23. My maths all right. Okay, and it's a positive and I'm happy. Why am I happy? It should be positive because it's supposed to be spontaneous. Right. So there's 1, 2, 3 marks, and this was worth 1, 2, 3, 4 marks. So we've got a lot of marks already, eh? Okay. Now, the only thing they can ask apart from this is they can ask you to make a drawing, right? They can ask you to make a drawing of this cell. So let me show the easiest way to make a drawing. So the first thing to say, if I've got magnesium in tin, there's my magnesium, and there is my tin, somewhere over here. Okay, I've got magnesium in tin, right. Then I said magnesium, having the more negative E0 value, is my reducing agent, which will oxidize, which will be my anode and my negative. Right. There I already can get 5 marks, because they can ask, reducing agent, oxidizing, what is the anode, which one is negative, and give me the half reaction. Right. And then obviously the other one is the weaker one, so this one should react to that side. It means it will reduce, so therefore this is the oxidizing agent. The cathode will be the tin, and it will be the positive electrode. Right. Now they're going to ask me to make a drawing. Now the easiest way to make a drawing is say, okay, what do I need for a cell? For a cell, you take your 2 metals and you put it into beakers. Right. So you put a piece of metal into a solution. What solution? If it is a magnesium metal, I put it into a magnesium solution, right. And if it is a tin metal, I'm putting it into a tin solution, right. So now I have this. And then I put a wire between the 2 metals. Why is that? So that the stronger one can send electrons to the weaker one. Okay. Will this happen? Well, once. But then this one is negative, right? So how can I make it to continue? I need to add a salt bridge. So I take this. This is a glass pipe, right? A round glass pipe that is just bent over. And I put in there potassium nitrate to make that water to carry current. Otherwise, you can't have a current going through there. You have to have a current flowing there. So what's happening over here is the magnesium is oxidizing. So what's happening? The magnesium metal is sending electrons to that weaker one. And what will happen with the magnesium 2 plus? The magnesium 2 plus that is formed is going into solution, right? So what will happen to this piece of magnesium? It will become smaller and smaller and smaller, because the atoms are becoming 2 plus and going into solution, right? What happens on the other side? Now you have electrons coming the zinc 2 plus in the solution will get that electrons and it will form a tin deposit over there. Right. So what will happen on this side? This will get heavier. Right. Heavier and heavier because you have new layers forming over there. Right. So you've got electrons traveling in that wire. A wire has got, do you remember metals? You've got delocalized electrons. Right. So over there you've got delocalized electrons traveling in the metal. What kind of charges do we have that travel in solutions? Anions and cations, right? Pure water does not conduct electricity. Why? Pure water, H&O, non-metals, covalent bond sharing. There's no charges, right? And remember, electric current is the movement of charges. So if you have no charges, no current, right? So what do we do to pure water to make it into an electrolyte, to make it something that conducts electricity? We put a salt in there, right? But here we've got a lot of salts. So it will be able to. So what happens is you've got negative electrons doing that. And once you get there, you get the negative ions. Now, what do we call negative ions? Anions. So you will have anions going through the salt bridge to this side that is called the anode. So you will always have anions going to the anode. Right. In the wire, it's only electrons traveling. But in the solution, you've got two kinds of charges. You've got cations and you've got anions. So in the wire, it will be only electrons doing that. But in the solution, anions continue the negative movement, and cations will do the opposite. They will go to that side. Right. So if you look back at this page, this is your summary for a galvanic cell. So what do? You start by getting your two reactions. Then you look who's the stronger one and make it win, right? The stronger reducing agent should oxidize, right? So it's oxidizing, it's making magnesium 2 plus. The weaker one obviously then have to do the other way around. No question. It must take the babies and babysit, right? There it is. It's staying put, right? So it's doing that. Half reactions, easy to write. Just remember single arrows, right? If you write a double arrow, you don't get the marks. Single arrows. Cell notation, I'll come back to you. Right? Cell notation, what do we have to remember? Oxidation, reduction, right? Double line represents your salt bridge, right? E0 value, you can get the cell EMF by using that equation, just substituting. The table is only true for standard conditions, and you have to be able to make a drawing. Are you fine? Sorry. Right, let me just say two things. Our time is so very limited. I'll also answer your question afterwards. I'll come to you once we've finished. But I just want to say, remember, they have been working very hard to make a live stream video. So if today went a little bit fast, because I know this is the first time you see this new work, right? For some, even the grade 11 work was new, but okay. You can go and you can work through the same things with the video, right? You can re-look at the video on YouTube, and then you can see it, right? So tell me, which was the best day? Monday with chemical equilibrium. Who choose Monday with chemical equilibrium? Who choose Tuesday with work, energy, and power? Okay, a lot of you. Who choose acids and bases on Wednesday? Right, quite a few. Who choose mole on Thursday? Right. And who chose the new work? You will tell me afterwards, eh? Right. Okay, guys. I hope you have a wonderful holiday, and I will watch out to see where you go in future. Right. Thanks. Okay. Bye.